Now we will study reinforcement learning. So reinforcement learning is a way to train an intelligent agent to take the optimal actions in a dynamic environment so that there is a reward that is maximized. So we have our agent. This agent is interacting with an environment through actions, so it performs an action, and this action on the environment produces some result, and this result somehow updates the internal state of the agent, and eventually it can produce a reward. So actually the reward may be immediate, or it can take some time to come. So these kind of problems, they are modeled with Markov decision process. So we have a set of states that the agent can be in. We have a set of actions that the agent can take. We have a probability transition matrix, so that we are currently in a state S. We take action A. What is the probability that the next state will be S prime? Then we have a reward. So what is the expected reward of taking action A in a state S? And we have a discount factor, and this discount factor controls how much future rewards are valued with respect to immediate rewards. Maybe we can have very small immediate rewards, but we can delay our reward because later we will have a bigger reward. So the goal of the agent is to learn a policy, that is policy pi, that is given the current state S, what is the action that we should take, so that we maximize the expected cumulative reward. So the problem is given or defined by this set of kind of inputs, not inputs, but variables, so states, actions, probability transitions, reward function, and discount factor. And the problem is to come with a proper policy. So to do that, we need a couple of functions. So one is, what is the value of a state? And we will call it, what is the value of a state if we follow the policy pi? So if we follow the policy pi, the value of the state S is the expected value according to pi of all the rewards. So we start in this state S. So S0, the first state, will be S, and then we follow our policy. So this is this expected value here. So we follow our policy. So given at S, we will take this action, because the reward that we expect from that action is whatever. So, and we move from one state to the next by changing the actions, and now we can compute the reward at each one of those steps, and then discount to the current time. So this discount factor, that typically is, let's say, 0.9 or 0.99. So that means that rewards that come very much later in the sequence, they are very little valued. Then we have the action value function that we will call Q. So Q is the expected return if the agent starts in a state S and takes action A following this policy. So somehow it is also related to that. But it is a simpler version, and the relationship between the two is this two. So the value of a state taking this action is the expected value according to the policy of the reward now, plus gamma, the value of S prime, and S prime is the next state. So to optimize, to find the policy, what we have to find, or we should find state value functions and action value functions, so Q and V, such that they satisfy the Bellman optimality equations. So that is, the value of a state is the maximum of Q of that state and taking an action. So the maximum taking the action, so the best action that we can take. So this can be expressed also this way. So the best action value function is the reward of taking starting with S. So this reward was an expected reward, so it is a reward taking the whole sequence, and so the reward of the state is an action A plus gamma, and then this thing, and this thing has to do with the probability of what is I think it is better described here. The value of taking action A in state S is the immediate reward plus the expected discounted value of the best action available in the next state S prime. And then we have these probability transitions. So because we can have a state, but the next state according to our action may be also random, so that is why we have here a probability distribution. Okay, so to solve V star and Q star, that are the best value and state functions, so what we can do is to follow this kind of dynamic programming. So we have to define what is V. So we start with some Vk, and then we define Vk plus 1 this way. That is just kind of similar to what we had here. And the policy iteration alternates between policy evaluation, so computing V according to that policy, and policy improvement, so choosing actions somehow that improve with respect to the current values in a greedy way. And these methods require full knowledge of the transition probabilities, which is often not available when you are doing reinforcement learning. And then you have to come out with, so this dynamic programming approach needs these probabilities, and because you don't know them, you have to solve or to find the best strategy, the best policy in some other way. And this other way are these Q-learning or SARSA. So these are called model-free methods. So you don't know what are the transition probabilities. So what this is called an off policy, this is called an on policy. So this Q-learning updates. So you start with some value that you associate to each one of the states given an action, and then you will update them. And this update has a learning rate and the reward, the immediate reward, plus gamma, so the discount of the best action that you can take. So it is the best action, so for the given S prime, you will take the best action A prime. So this is updating Q SA using the maximum Q value that you will have in the future. But the problem is that you don't know what the best value will be. So this maximum here, normally you don't know. So you have this SARSA, and this SARSA takes a next step, sprime, and then updates QSA according to this. And these two, they use something that is called epsilon greedy exploration. So epsilon greedy exploration is this thing. So let's say that you are given some current estimate of what the values of the different actions are, states and actions are. So you are given this QSA, current estimate of QSA. So with probability epsilon, you take a random action and then you explore what happens. With probability 1 minus epsilon, you take the best action that you can have according to your current values. So your current values of each one of the states are given by Q, and then given that you are in S, you take the best action you know for the moment. And this exploration probability is typically something around 10%. So here what you would do is you take, so these two are using epsilon greedy, and epsilon greedy, this one is taking whatever S prime is, this one is updating, assuming that you will take for the next S prime, you will take the best A prime. So where is deep learning here? So deep learning comes at learning the different functions that appear. So for instance, we could approximate QSA, so the value of the state S with action A, with some parameter vector and some features. So you have to transform the state and the action to some features. So it is some projection, and here you could have a neural network to do that, and then you simply multiply by a feature vector, and then this is somehow this QSA, and this QSA you have to update, and we had here the rules for updating them. So another approach would be to train QSA with a loss function. So a loss function is this loss function that depends on the weights of the neural network, and somehow it is learning the QSA function, and you have it with some kind of internal reference, this loss. You don't know what is the ground truth, so you define a loss function that somehow is stable. This is what this goal function seems to be saying. The other possibility is, instead of learning QSA, directly to optimize the policy function. So now your policy will be the neural network. So given a state, it will produce what is the best action. So it will produce a vector for the actions, and this vector for the actions you will take kind of the same as we did with the large language model. So they produce an output score, and then you choose randomly for those scores according to the score value, and that those methods, they are trained using this policy gradient method. So policy gradient is what is the expected value according to my policy of the value, this Q, that I'm not learning, I'm just inferring. So the neural network is on the policy, not on the learning of the value function. And then this probability, that the probability of taking the action, not probability, the policy, So this policy that is given this state, what is the next action? And this one depends on the weights of the neural network. So here we have an example of that. So this example, here you have more other examples, but this one is, okay, so given this sinusoidal or periodic behavior, we are given a history of what is the ratio between the previous samples and the current sample. So current sample and the next samples here. So this is t minus tau, and there is an extra shift here. So that is what are the values in the future, and then given this state, we have to decide whether we should or we think that the curve is going up or the curve is going down. So we have to follow the trends. So this is the result. So here this example is solved in this notebook, and what we see is how the reward is growing. So for the beginning, it cannot learn quite a lot, but so after 200 iterations, somehow it learned how to optimize that, and then we have a smaller loss. So this is a very first introduction to reinforcement learning and using neural networks. So again, we have not seen all the details. This is a field in itself. So, but we see that the neural networks come into the evaluation either of the value functions or the policy.